Welcome to Learning Assistant app. Have you ever wondered how chemists weigh individual atoms when they're far too small to see, even with the most powerful microscopes? It feels like trying to count every grain of sand on a beach, using only a standard bathroom scale. To solve this, we need a bridge between the microscopic world of atoms and the macroscopic world we live in. That bridge is the mole. Think of the word dozen. When I say a dozen, you immediately think of the number 12. Whether we're talking about eggs, donuts, or cars. A mole is exactly the same thing, just a much larger number. Let's look at this value appearing on the screen. 6.022 times 10 to the 23rd. This is Avogadro's number. To visualize how massive this is, imagine if you had a mole of marbles. They would cover the entire surface of the Earth to a depth of over 50 miles. Yet, because atoms are so incredibly small, one mole of water, that same 6.022 sextillion molecules, fits easily into a single small glass. Notice how the mole allows us to count particles simply by weighing them. But what if our substance isn't a solid or a liquid? What if it's a gas? Picture 3 identical balloons. One is filled with helium, one with oxygen, and one with nitrogen. Even though oxygen molecules are much heavier than helium atoms, Avogadro discovered something profound. At the same temperature and pressure, equal volumes of gases contain the same number of particles. Let's look at the molar volume. Under standard conditions, 1 mole of any ideal gas occupies exactly 22.4 liters. Imagine a large cube about the size of a standard microwave. That's the space 6.022 times 10 to the 23rd gas particles will fill, regardless of what the gas actually is. Now let's move into the lab. Chemists often work with solutions, liquids, where something is dissolved. This is where we encounter molarity. Watch what happens as we add blue copper sulfate crystals into a flask of water. Molarity is simply a measure of crowdedness. It tells us how many moles of a substance are packed into 1 liter of solution. If we have a 1 molar solution, we know exactly how many millions of trillions of molecules are floating in every drop. So how does it all fit together? Imagine the mole as the central hub of a wheel. From this hub, we can travel in any direction. If you have the number of particles, Avogadro's number is your path to the mole. If you have a volume of gas, the molar volume of 22.4 liters is your path to the mole. And if you have a liquid solution, molarity is the connection. The beauty of the mole is that it turns the invisible, chaotic dance of atoms into something we can calculate with perfect precision. It is the universal language of matter. The next time you take a breath, consider this. You are inhaling roughly 1/10 of a mole of air. That's more molecules than there are stars in the observable universe, all managed by a single, elegant number.